Good afternoon, sir.
Good afternoon, sir.
Good afternoon. So I have started recording. You can give your attendance. Okay. Okay. So in the last class we have completed chelation therapy. Any question regarding chelation therapy, or I should move on? If you have any question regarding chelation therapy, you can ask. Okay. So I move on to the next part, which is application of radionuclide. That means radioactive nuclei in imaging and diagnostic. So radionuclide can be used for medicinal purposes, and there may be two kinds of uses. Some radionuclei are used for imaging purposes, and some radionuclei are used for diagnostic purposes, meaning killing of the cancer cells, etc. So, first question is, which type of radioactive nuclei are suitable for which type of purposes? Now, all of you know from your school knowledge of radioactivity that alpha and beta rays has got less penetrating power because they are particles more or less. Whereas gamma ray, it is shorter than X-ray in terms of wavelength, and it has got much penetration power. So since gamma ray has got penetration power which is comparable or even greater than X-ray, so just like X-ray, gamma ray, those nuclei which can use gamma ray, they can be used for imaging purposes. So gamma emitting nuclei are used for imaging purposes because gamma ray penetrates to most of the tissue or even the bones. That's why gamma ray is not useful for treatment of cancer cells, for destroying cancer cells. On the other hand, alpha and beta emitters, alpha and beta ray, because they are less penetrating, they interact more with the cell material, more strongly with the cell material, and as a result of this, alpha and beta emitters are used for diagnostic purposes. এইটা হবে এইটা হবে এইটা হবে বলে পাপা বলে এইটা হবে ওইটা হবে তখন আমি ক্লাস নিই না বুঝেছেন যেখানে শরীরটা যদি প্রপার ওয়েতে এইটাই তো এই যে কোথায় হলো লাস্টে হ্যাঁ এইটা হবে হ্যাঁ এইটা হবে ওইটা হবে এটা খুলে দিয়েছি আপনাকে. So alpha and beta emitters are used for diagnostic purposes because the alpha and beta rays can, because of their less penetrating part, they can interact with the cell material and they can damage the cell material. So those radionuclide which will be alpha or beta emitters, they can be used for diagnostic purposes. Now, what do you mean by therapeutic radiopharmaceuticals? That means radiopharmaceuticals which can be used for medicinal purposes. Usually they are radio level molecules. Remember, in most of the cases we do not use simple radioactive metal ion radioactive element, but normally a radioactive element is incorporated in a molecule, and that molecule is actually used for radiotherapy. There are exceptions, but in most cases, radio-labeled molecules are used, and they are used for delivery of therapeutic doses of ionization to specific disease sites. Now, there are three ways in which radiation delivery can be done. One is external radiation. That means if you have some cancer or some tissues which need to be irradiated with some radioactive radiation, if that tissue is or if that tumor is in the outside organs, so they can be treated by external irradiation, right? So they are easy to treat relatively because external irradiation is sufficient for them. But this external irradiation is not useful for treatment of tumors or cancers inside the body, or for metastatic or secondary cancer, because most of the cases metastatic or secondary cancers occurs deep inside the organs, and so for treatment of them, the external irradiation system is not at all suitable. Then in some cases what is called brachytherapy, where sorry, where a radioactive nucleus is usually co-crystallized with certain innocent crystal, and those crystals are used as seeds, right? They are implanted as seeds. For instance, suppose you have a throat cancer or in this region, so sometimes some cobalt 60 source is implanted on your cancer cells for a certain duration, and then it is removed. So it can be implantable seeds, which can be called brachytherapy, or it may be systematic administration of certain radioactive molecules in the form of injections. So, I don't know what happened. Sorry. I'm sorry. Please, all of you, please switch off. What happened?
Sir, you are not audible properly. There are two simultaneous meeting in
Okay,
going.
okay. Just
वो दोनों बंद कर दिए.
okay. So, can you listen to me?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. So, a third option will be administration of certain radioactive molecules in the form of, say, intravenous injection or oral digestion, etc., etc., right? So, systematic administration of small organic or inorganic compounds that can be done. Now, radiotherapy has been used over 4 to 5 decades. One of the most extensively used radioisotope is iodine 131, used for the treatment of thyroid cancer, and more recently, strontium isotope, strontium 1889, or sodium phosphate, along with sodium phosphate, for the treatment and relief of bone cancer or bone metastasis. Okay. Now, in this table, this very important table, where we have before going to this to that table, let me first of all, like chelation therapy, here also there are certain conditions. All radionuclei cannot be used for medicinal purposes or as radiopharmaceuticals. There are again certain conditions a radiopharmaceutical must satisfy in order that it can be used as a radiopharmaceutical. The first condition is obviously the radiopharmaceutical should not be very toxic towards the body, right? Because if anything is very toxic towards the body, then instead of doing good, it will do more harm, right? So the radiopharmaceutical which is being used should not be highly toxic, should be tolerable to the body. Obviously, it will have some toxicity, but toxicity should be tolerable. Second thing is that it must have optimum half-life. Now, what is the optimum half-life? You see, the half-life should be such that it can be produced in a reactor, it can be transported to a hospital, and it can be used for medicinal purpose. But half-life should not be so long. That means if the half-life is very long, what will happen? That means the intensity of the radiation that is being emitted will be relatively low, and it will remain inside the body. The radiation background will remain inside the body for a long time. So we again want an optimum condition where the half-life should not be very high, very long, and half-life should not be too short. There should be an optimum half-life region, and this optimum half-life region is usually, say, from 5 to half-life should be greater than 5 to 6 hours, and it should be less than 8 days, less than equal to 8 days. So an optimum half-life is around 5 to 6, starting from around 5 to 6 hours to around say 8 days. This is the optimum level, because if the half-life is more than 5 to 6 hours, then it is easy to handle that radioisotope, because you have to transport it from a cyclotron or a reactor, and then you have to process it, and then you have to administer it. And if the half-life is less than 8 days, it means that the radio emission is relatively strong, and moreover it will decay rapidly, so that if multiple radiation treatment is required, you can give once the first dose decays, you can give a second dose of radio pharmaceutical. So it should not be very toxic, it should be readily available, obviously, right? It should be readily prepared in a cyclotron or in a reactor, and its half-life should lie between, say, 5 to 6 hours and 8 days. So, keeping this thing in mind, we have tabulated some of the most important radionuclei which are used for as radiopharmaceutical and their uses, and among them some of these nuclei I have marked with red. These are most important. All of them are important, but among them, those radionuclei which are marked with red, they are most often used. So you can see that potassium 43 isotope. It is mainly beta emitter along with gamma emitter, right? And this gamma imaging can be used. So half-life is 22 hours, and it can be used because potassium, is required for heart, right? So your heart pumping requires appropriate balance of potassium and sodium. So it can be used for heart imaging. Cobalt 57, it is a gamma emitting isotope. It can be used for imaging, particularly if you have a vitamin B12, chronic vitamin B12 deficiency. Then to understand the mechanism of transport of vitamin B12 in your body, sometimes this cobalt 57 isotope may be used. But more important is cobalt 60. Among the two cobalt isotopes, probably cobalt 60 isotope is more important. It emits both beta and gamma. The beta ray half-life is 5.26 years, so it is relatively long, right? So that means the emission is not very intense. So that's why it is better for imaging purposes, but for therapeutic purposes it is not so good. But still, in many cases, this beta emitting power of the cobalt 60 is used for therapeutic purposes. But as I am telling you, since the half-life is relatively long, so it has got its disadvantage also. Particularly, the intensity of the radiation may not be very large. So depending on the requirement, doctor may prescribe cobalt 60 isotope treatment. Then gallium 67, again a very important radioisotope that has come up and that has replaced in many cases these cobalt isotopes. It is purely gamma emitting, unlike this cobalt 60, which is gamma as well as beta. So this is better for imaging purposes. Half-life is 78 hours, though it is more than the optimum, but it is much obviously less than either say cobalt 57 or cobalt 60, and so it is now a very preferred isotope for tumor imaging, particularly for inflammatory tissues, right? So for inflammatory tissues, imaging this gallium-67 radionuclide is very important. Then ruthenium isotope. Ruthenium is a congener of iron. It is below iron in the periodic table. So ruthenium 97. It is a gamma emitting isotope. And again, half-life is 69 hours. It can be used for imaging of tumor and liver. And the advantage of ruthenium is that since ruthenium is in the same group as iron, so ruthenium radiopharmaceuticals are well tolerated in our body. Toxicity is much less compared to say gallium, because ruthenium is very similar to iron in uh, many of its chemical behavior. So ruthenium can be tolerated in our body. Now, probably the most important radioisotope are these two: technetium 99M and iodine 131. Uh, Now, this has got tremendous importance. Technetium 99M. This M stands for, M may be called a metastable, but generally M is called man-made, because this isotope is not naturally occurring. It is man-made. Technetium 99M. It is a gamma emitting isotope, and it is probably in nuclear most. It is probably this isotope is probably the largest use in nuclear medicine. And many important hospitals and nursing homes, they have got technetium reactor in their in their premises, where they produce this technetium 99 isotope, and it is used for variety of imaging, but particularly for heart imaging and brain imaging. Technetium 99M found to be superior, very superior, and we shall discuss technetium 99M a little bit probably in the next slide. Then two iodine isotopes are used. Iodine 123 is a pure gamma emitter which can be used for thyroid imaging, but more important or more widely used iodine isotope is iodine 131, which is both a gamma and beta emitter. Half-life is 8 days, and it can be used both for gamma ray, can be used for imaging using a gamma camera, and because it is also a very good beta emitter, so it can be used for thyroid cancer also, right, for treatment of thyroid cancer, thyroid therapy. Then we have rhenium 186, again relatively new radioisotope, which is both beta and gamma emitter, but it is more a beta emitter than gamma emitter because it has been marked bold, means it is more a beta emitter. Half-life is 89 hour, and it is one of the preferred modern beta emitter for therapy. Right, lead to 212. It is not much important nowadays because of toxicity of lead. It is both again, and it also emits alpha, beta, gamma emit, and half-life is also not very good. So it can be used for therapeutic purposes, but gradually it has been made obsolete. Again, this is a relatively new isotope, indium 111. This is a pure gamma emitter. So this is a pure gamma emitter, and it is used for radioimmunotherapy. So you can see that modern in terms of modern radiopharmaceutical, two very important isotopes have come up. One is indium, which is a gamma emitter, right? Gamma emitter, and another is yttrium 90, a beta emitter, right, which can be used for radiotherapy. So indium 111, which is a gamma emitter, it can be used for it can be used for imaging and radioimmunotherapy, and yttrium 90, which is a beta emitter, it can be used for radiotherapy. So these are the most important radioisotopes. Particularly, you just give more importance to the isotopes which I have marked as red. And we have also copper isotope, copper 67, which is beta and gamma emitter, and it can be used for radioimmunotherapy. So please give emphasis on the isotopes which are marked red. Now, when you are asked a question, very often you are asked a question like this: that name two radioisotopes which can be used for imaging and two radioisotopes which can be used for therapeutic purposes. Now, very often I find that the students, because of their confidence, obviously, they mention cobalt 60 under both therapy and imaging. Uh, though they get marks, but they do not get full marks because cobalt 60 uh, gradually, previously it was used for therapy much, but nowadays with discovery of some new isotopes, cobalt 60 is more an imaging purpose, and as you can see that its half-life is too long, right? And as a result of this, cobalt 60 is now more of imaging rather than therapy. So choose it in a proper way. Same isotopes should not be used as an example for both imaging and as therapy. You try to remember two isotopes for imaging purposes and two isotopes for therapeutic purposes. And you must also remember you need not remember their half-life, but what are the emissions? Are they gamma emitter or beta emitter? That you must remember. But you must remember technetium 99M. So one is already there for imaging. You have iodine 131, which can be used for therapeutic purposes. So these two isotopes you must remember, and among the other you remember any other two, right? Now I come to this technetium, because I have told you technetium nowadays has become one of the most important radioisotope in nuclear chemistry. Now what happens that uh, we may say that what happens in a reactor, first of all, in a reactor, this is molybdate, MoO4 2 minus, right? So you take say sodium molybdate or ammonium molybdate, and here molybdenum is 98, right? The atomic mass number is 98. Now, when there are a variety of ways in which you can generate technetium, but this is one of the most easy way. You bombard it with a slow neutron, and this molybdenum become molybdenum 99. This we are not. I am not writing this oxygen, etc. So molybdenum will be converted to molybdenum 99. Now this molybdenum 99, then what happens? It emits a beta. It emits a beta emitter. Now when it emits beta, it forms technetium 99M. Now what do you mean by technetium 99M? So that means suppose we have, this is the molybdenum 99 isotope. Now when it emits beta, it forms technetium 99M. This technetium 99M can emit a gamma radiation and form 99 technetium. So we can say this technetium 99 and technetium 99M, they are called nuclear isomers. That means they have got the same mass number, but the difference is that their nuclear energy levels are different. Technetium 99M is produced where the nuclear energy level is slightly higher, and technetium 99M emits gamma radiation to come back to a relatively ground technetium 99 nuclear energy level, and this technetium 99 in turn emits a beta radiation and it is converted to ruthenium 99, right? This is the way, and this half-life of molybdenum isotope, it is around say 60 hours. So you can take molybdate, bombard it with a neutron in a nuclear reactor or a cyclotron, and then produce this radioactive molybdenum. Because half-life is relatively large, so it can be transported from the reactor or cyclotron site to the hospital, because half-life is quite large. And this technetium 99M, it has got half-life of around 6 hours, right? So once you bring it to the hospital, in the hospital what happens? They have a so-called technetium reactor. It is nothing. It is not a nuclear reactor. What they have? They have, suppose they have a column, right? They have a column, So with say stopcock here, right? And so they here there are some column material is stacked, right? They inject the 99 molybdate from upper side, and they elute, they actually charge the column with the sodium chloride. What happens? This molybdate is decaying and it is producing technetium. So through the column, you will get the molybdate will stuck in the column, and through the column you will get mainly 99 TCO4 to TCO4. So minus, so you get this is the way. So it is nothing what their nuclear, what their hospitals call as technetium reactor is nothing but a column, column chromatography column, through which they charge radioactive molybdenum, and like it is like a bullet, for instance, right? So through the upper mouth you charge radioactive molybdenum. This bullet like thing is loaded with some column material, and it actually adheres the molybdenum more strongly than technetium. So molybdenum stuck here, and the technetium come out when you elute this column with sodium, the saline salt, saline solution. The technate comes out, and the patient is treated with this technate. Or you can use this technetium for variety of purposes. Now, apart from this technate, which can be used directly for radioactive injection. Now, technetium compounds has also been formulated, and it has been found that technetium, you can prepare technetium in the +1 state, or you can prepare compound of technetium in the +5 state, right? And it was found that the imaging property of the technetium 1 and technetium 5 are somewhat different. So this is an example of commercial technetium 1 complex, which is extensively used for heart imaging. Its commercial name is cardiolite, which is a heart imaging agent. What is that? A technetium 1, which is hexa-coordinated, 6 coordinated with 6 isocyanide ligand. RNC is isocyanide. You know in the organic chemistry that when RC, this cyanide is RCN and isocyanide is RNC, right? So this is an isocyanide complex, technetium isocyanide complex, where R is your disorganic group, right? So it is a kind of methoxypropyl group, right? So you have one, so methoxy or methoxybutyl group, you can say methoxybutyl group. There are 4 carbon atoms and there is one methoxy group, so methoxybutyl group. So R is this group. So this isocyanate complex where technetium is in the +1 oxygen state, obviously overall complex, since the ligand is neutral, overall complex has got a +1 charge. So this technetium 1 complex found to be very important for heart imaging. Now on the other hand, you can prepare compound of technetium in the +5 oxygen state also. In the +5 oxygen state, here technetium is coordinated to 4 nitrogen donor ligand and 1 oxo ligand, right? 1 oxo ligand. So you have so you have technetium in the +5 oxygen state, because here there are 1 hydrogens which are deprotonated and 1 oxime hydrogen is also deprotonated. So 2 + 1 3 + 1 4 + 1 5 coordination. So there are 2 oxime moieties, out of which 1 oxime hydrogen has been deprotonated, and initially in the ligand these nitrogens were protonated in H protons. Now on coordination this NH has been converted to N-, so you get 1 minus charge from here, 1 minus charge from here, 2 minus charge from here, and 1 minus charge from here. So it is a technetium 5 complex, right? And this technetium 5 complex, whereas technetium 1 complex are specific for heart imaging, this technetium 5 complex can be used for heart imaging as well as cerebral imaging as well as renal imaging, right? So This has got multiple applications. You can use it for heart imaging, you can use for cerebral imaging, that is brain imaging, you can use also for renal imaging, right? That is imaging of the kidney, kidney cells. So technetium is very important radioisotope. So, and when you mention any radioisotope for imaging purposes, you must have technetium among the examples because probably this is the most important radioisotope for imaging purposes.
Sir,
Now,
I have a question, sir.
yes, any question?
Sir, why you are writing, sir, 99M on the technetium, sir? What does M means?
M means it is man-made, right? M has got two meaning. One is the normal accepted meaning is M is man-made because this isotope is not naturally occurring. It has been made by man. Two American scientists. I hope you have heard their name. One is very famous nuclear chemist G.T. Seaborg, G.T. Seaborg, and Emil Segre.
Yes, sir.
Right, Emil Segre and
Emil Segre heard.
Emil Segre and Glenn Seaborg. These were the two American scientists working in the, I think, Oak Ridge National Laboratory or something like that. I don't remember exactly the lab. They first discovered this technetium-99M isotope, and it was not a naturally occurring. It never existed in nature. It has been prepared synthetically. That's why it is called technetium-99M. But some scientists also call it as technetium-99M as metastable because here technetium-99M is metastable because it is in the higher state, it is in the excited state, nuclear excited state. It is emitting to come to the ground technetium-99 and then it is emitting beta. So this compared to this normal technetium-99, which is a beta emitter, technetium-99M is a gamma emitter because it is a nuclear isomer of technetium-99, and so it can be called this excited state can be called a metastable state. So it has got a twin meaning. You can call it technetium-99M means technetium-99 man-made isotope, and this man-made isotope is actually a nuclear isomer of the more stable isotope technetium-99. In that sense, it is a metastable isotope. Is it okay?
Yes, sir, understood.
Okay. Now, sometimes, obviously, again, when you give a nucleus or radiopharmaceutical to a particular person for treatment, there will be indiscriminate distribution of there is chance of indiscriminate distribution of radiopharmaceutical to various parts of the body. That means, apart from the targeted organ, it may go to the other organs also, and that's why nowadays this so-called radioimmunotherapy is coming into play. Now, what is radioimmunotherapy? Where you have suppose this is a radionuclide, you complex it with a chelating agent, right? And then the chelating agent is coupled with what is called PKM linker. PKM linker means pharmacokinetic modifier. Pharma P stands for PKM stands for pharmacokinetic modifier. That means you modify its pharmacokinetics. How do you do that? You couple it with certain biochemical which are specific antibody for a given organ. Suppose you want to target it to a kidney cell. So you try to couple this chelated radiopharmaceutical with certain biomarker which are specific for the kidney. If you want to direct it to the liver, then go for the corresponding liver specific antigen, etc. So this pharmacokinetic modifier are organ specific antibodies, we can say, right? Or organ specific antigens which targets a specific organ. So in the radio immunotherapy, people take the radiopharmaceutical, couple it with a corresponding immuno or bioimmuno agent which can target a specific organ, and then this molecule is thrown inside the body so that it will bind specifically to the organ which is desired. Okay. So this completes our discussion on actually radiopharmaceutical. So I again tell you that you you go through this table and you try to remember that two radioisotopes, at least two radioisotopes which are used for imaging purposes, two radioisotopes which are used for therapeutic purposes, and you try to understand what are the we ask what are the criteria, right? So if I ask you what are the criteria for imaging, you must say that it must emit uh, gamma rays. What is the criteria for radionuclide to be used for therapy? Obviously, it must be able to emit alpha or beta ray, preferably beta ray. That is the thing. And half-life should have optimum value. It is between say 5 to 6 hours to 8 days. But so many in many cases, this strict guideline is not obeyed because that kind of radioisotope may not be found for a particular kind of nucleus for a particular kind of element. So these some of the radionuclide I have told. So this most important is technetium 99M. We have gallium 67 and cobalt 60. We have iodine 31, and then gamma emitting isotope indium 111 and beta emitting isotope yttrium 90. These are, we can say, most important radioisotopes in modern radiopharmaceutical industry. Okay. Next, we shall go to uh, MRI imaging. Again, we have a radionuclide imaging, and we again probably more important is MRI imaging because it is used more frequently than radionuclide imaging. So I have written here that MRI imaging is growing at a rate of zero point 0.5 million US dollar per year, right? So and MRI contrast agents are one of the fastest growing diagnostic pharmaceutical that is being used, right? So MRI is a very important MRI scan is very important for diagnostic purpose, and it is rapidly growing continuously, and as a result of this, MRI contrast agents are also growing rapidly. Now, through MRI, what we can look at, particularly strokes in brain, right? Damage of the blood vessels, which is called angiography, damage of heart tissues, and it is one of the most sensitive technique for detection of breast tumor. So MRI has got tremendous application for stroke, for blood vessel angiography, as well as for detection of tumors. And also detection of many tissues also, in sports medicine it has MRI has got a tremendous application. Now what is the theory of MRI imaging? Theory is not very difficult. We know that in a hydrogen atom there is only one proton, and this proton can have plus of spin or minus of spin. When it is plus of spin, it is actually aligned along the external magnetic field. When it is minus of, it is aligned along the opposite to the magnetic field, right? So this is these orientations of the two plus up and minus up over spins with respect to an external magnetic field. Now, when you have no external magnetic field, then these two orientations has got no meaning. So obviously, Mi equal to plus half and Mi equal to minus half, they have got identical energy. But when you apply a magnetic field, because plus half corresponds to alignment of the nuclear magnetic moment along the external magnetic axis, so obviously this actually creates a situation which has got lower energy. And when a magnetic moment is aligned antiparallel to the external magnetic field, it has got higher energy. So we have Mi equal to plus half has got lower energy, and Mi equal to minus half has got higher energy in the presence of an external magnetic field. And this energy gap is not very high, and so this energy gap can be bridged by a radiation which is in the microwave region. Usually, you can use a microwave of the order of say megahertz, 600 megahertz or 100 megahertz or around 600, say 100 to 1000 megahertz radiations can be used to bridge this energy gap. And depending on the magnetic field, if you have strong magnetic field, then you produce you give higher megahertz radiation. If your magnetic field is weaker, that means if your magnet is weak, then you will use a relatively low megahertz radiation. But obviously, if you have higher magnetic field and higher megahertz radiation, that creates a more clear image, right? So the clarity of the image increases. Now, what happens that in the MRI imaging, what you do, you first of all, uh, so the patient goes, right, and in our body, in a human body there is 70% water. So that means we are looking at the protons of these water molecules, right? Protons of this water molecule. Now, when you want to scan a particular tissue of a body or particular organ of a body, what is your principle is that initially you apply a magnetic field so that the protons will have the mi equal to plus half and mi equal to minus half. These orientations have got different energies, and now you give first of all a strong pulse of strong pulse of microwave radiation, so that most of the protons from ground state goes to the excited state. And then you remove the pulse. That is, pulse is a short duration pulse, and then you remove the radiation source, or you switch off the radiation source. Now this, in the excited state, we know, like the hydrogen atom problem which we have discussed, which we have studied earlier, they come back to the ground state. So excited nuclei come back to the ground state from mi equal to minus up to mi equal to plus up. Now this coming back to the ground state is known as relaxation phenomenon. So we are giving radiation to flip the spin of the proton from plus up to minus up, and the proton in turn will relax, and during relaxation it will emit radiation, right? It will emit microwave radiation, and this microwave radiation which is being emitted by the protons of the water molecules of your body, that is being monitored. And looking at the relaxation pattern, the experienced MRI imaging specialist can actually predict what are the things that are good or bad in your particular organ. So he actually looks at the emitted radiation, right, that is coming from your body after the protons has been excited. And obviously for complete imaging you require several pulses. So first of all you give a pulse, wait for the relaxation, you give another pulse, wait for relaxation. In this way, several hundred or thousands of pulses are used ultimately to gather a signal of sufficient intensity. And different organs, water molecules in different tissues or different organs of your body has got different relaxation rates. So depending on the relaxation rates, depending on the nature of the organs which is being scanned, you will have different images, and the specialist, by looking at the images, will tell you what is the situation in your tissue or in your organ which is being scanned. Now, it has been found that in many cases, you see, doctors may prescribe MRI imaging without a contrast agent or with a contrast agent. When MRI is done without a contrast agent, then image may not be very sharp. On the other hand, doctors, when they want to get details feature of a particular organ or tissue, they generally prescribe MRI imaging with a contrast agent. Now, what is the function of the contrast agent? Contrast agent actually facilitates relaxation. And as the relaxation is facilitated, because we shall not go into the theory, but if the relaxation becomes faster, then the clarity, sharpness of the image increases, right? and the signal intensity also increases. So in MRI imaging, in MRI contrast agent, the contrast facilitates relaxation of the excited protons, I mean excited nuclear proton, excited nuclei of the protons coming back to the ground state, and it actually creates more sharp signal so that it can be interpreted better. Okay, now there can be, I will not again go into the details. Generally, there are two kinds of relaxation, what is called a spin lattice relaxation, where excess energy is given. Spin lattice relaxation, as the name implies, that the excess energy stored by the spin, when it is coming back to the ground state, excess energy is given to the lattice. That means given to the surrounding, given to the solvent, right? So that is called spin lattice relaxation. And sometimes there is another relaxation called spin relaxation, whereby this excited energy, the energy which is being given out is picked up by another proton from the ground state. So overall, in that case, when we have a spin relaxation, overall number of the excited nuclei does not change, but it actually changes the phase of the signal. So doctors may often look at both T1 relaxed signal and T2, that means one relaxation is called T1, spin lattice relaxation, another relaxation, spin relaxation, is called T2. So a doctor may want to look at both kind of relaxation images or one kind of relaxation images. So depending on the circumstances, the radio, the doctor who is actually acquiring the image may actually acquire both kind of relaxed images, or he may acquire particularly T1 relaxed images. So it can be done in various ways, but theory is that as the nature of the tissue increases, if the tissue damage occurs, then obviously there is more swelling, and swelling causes accumulation of more water, and obviously the nature of the image of a damaged tissue will be somewhat different from that of undamaged tissue, right, normal tissue. And so one may distinguish a damaged tissue or damaged organ from a undamaged organ or undamaged tissue. Now, what are the contrast agents that are actually used for MRI imaging? Obviously, I have told you that what is the function of the contrast agent? Contrast agents will facilitate this relaxation, coming back of the excited spin to the ground spin. So, in order to interact with this nuclear spin, we have complexes, metal complexes, which has got a high electron spin. They are used. So if you can choose metal ions which has got a large number of unpaired electron, then those unpaired electron will produce a, again, magnetic field, right, because of the unpaired electron, and that magnetic field will interact with the magnetic field here, and it will facilitate relaxation. So for contrast agent, generally those metal ions are used which has got a large number of unpaired electrons, and generally two or three metal ions are used. We have gadolinium. This is a lanthanide metal ion, gadolinium, which have 7 unpaired electrons, and manganese 2 ion or ferric 3 ion, which have got D5, that is 5 unpaired electrons. But most important, probably in 98% cases, this gadolinium ion, some kind of gadolinium complex is used as imaging agent. Now, what are the ligands that are used for gadolinium? We have DTPA. You remember DTPA. We have already discussed in our previous class, also here, plutonium. So diethylene triamine pentaacetic acid. So same ligand, diethylene triamine pentaacetic acid, right? So this is the ligand which can be used. So 1, 2, 3, and then this acetic acid group, there are 4, so it is 7 coordinate, 7, it actually can bind in a 7 coordinate fashion. So this is the binding mode, and lanthanide ions can bind, can have large coordination number. So here gadolinium is 8 coordinated, so 7 coordination is coming from this ligand, 3 nitrogen and 4 carboxylic acid groups, and 1 coordination is coming from water. And this water is very important, because this coordinated water will undergo exchange with the water of your organ, or of your tissue, and it will increase the influence of gadolinium on the relaxation process. So you require some coordinated water for influential contrasting agent. So that's why this kind of metal ions are used where we have a coordinated water. Or we can have another ligand here where almost similar, but here it is called DOTA. Again, very, why DOTA? Because it is a 12-membered ring, so dodecan. Right? Do stands for dodecan, and it is tetraacetic acid. So we have 1, 3, 1, 3, 5, 7 tetraaza. There are 4 nitrogen, 1, 3, 5, 7 tetraaza dodecan, and then we have the tetraacetic acid. So here again 4 nitrogen and 4 carboxylic acid, so it is 8 coordinated, and gadolinium here is actually, you can find that 9 coordinated. So there is 1 water again here, and that can again undergo exchange with the water in your body, and it be used for contrast agent. So these two complexes, gadolinium DOTA and gadolinium DTPA, these are the most useful contrast agent. Now again, you can tune your, I shall finish it here. So again, you can tune your contrast agent. So here, as an example, this is a contrast agent whose commercial name is MS325. Here you can see that it is slightly modified. This DOTA ligand, it is coupled through this phosphate bridge to an organic compound, right? Now, the usefulness of this coupling is that this particular, after binding to this organic moiety, this can easily bind, this gadolinium complex can easily bind to the albumin of our blood. And since this complex can specifically bind to the uh, one particular constituent of the blood. So this, but after coupling of this particular organic species, this MS325 can be used very. It is a very good reagent for angiography. That means the you can monitor the flow of blood through certain artery or organs. So it can be used for angiography. So this is a very important angiographic agent, MS325, after certain modification of the original gadolinium DTPA complex. And there are certain manganese complex which also was used for imaging purposes. It is called manga-4DP, or the commercial name is Tesla scan. Again, a manganese complex was used, but nowadays this has been withdrawn for last 5 years, and now almost solely these gadolinium complexes are being used for the imaging, MRI imaging purposes. So I end my discussion here. Right. So next class we shall consider metal complexes as